Okay, welcome. Let's begin. Um, I'm feeling a little confused just now. Do you actually see the more recent screencasts on our YouTube channel? Because currently I don't, which I can't explain. So the link from the course page works for me. I guess you're not the target group for the screencasts. You who are here, you at home, you just tell me. All right, we haven't had any reports, so I'm assuming that things work out as they should. Another remark or apology, we're running 2 days late posting the final obligatory assignment for this course, problem set 3B, which will be on PCFG parsing with the pen tree bank. It's coming tonight, promise. A large number of people submitted on Sunday, but also an unusually large number of people fell ill and required a few days extension. I'm guessing it must be the time of the year or Dagen et Ifi, or I hope it's not about that problem set that made you sick. If so, please tell us next time. All right. So that's the announcements. Then let's get started on content. We'll move to what is often called generalized chart parsing today, a framework for parsing with context-free grammars, and then we'll adapt the Viterbi algorithm to parsing with syntax trees. And I feel we have a relatively full program today. Let's see how we get through that. And then this coming week, we'll have a little more leisure time. It's the last content lecture. There will be some wrapping up, setting things into perspective as regards parsing. Some of you have asked, okay, what's the utility actually? And I'll try to give you at least some pointers. And there will be a quiz. For a few more bonus points, mostly on our most recent topic, parsing. And there will be some live coding, so really a mix of the most attractive things we can offer you in a lecture. And then probably 2 weeks later, actually, that is 3 weeks from now, we'll hold our final exam preparation lecture. We haven't concluded with that, but 2 weeks from now, Erik actually couldn't be here. Erik now has the privilege of representing, well, of being a member of a reform group here at the department that is about to decide which programming language would be best suited for the introductory teaching to programming. And so that's an important role, of course, and that committee meets on Wednesdays at 2. So he is apologetic for not being here, but has the greater good to consider. It's likely not going to be Common Lisp or Scheme. But what it actually will be is yet to be decided. And so 3 weeks from now, Erik actually could join us then for that final wrap-up exam preparatory lecture, and we'll make up our minds and then post an update to the course schedule. So it's possible that you'd have no lecture 2 weeks from now, and that would be then extra time to complete the last assignment, which is coming tonight. All right, so looking back briefly, we brought home the notion of context-free grammar, relatively briefly looked at this notion of annotated training data for supervised machine learning in the syntactic parsing space, and looked especially at the pen tree bank. So now you have been introduced to the full picture of a resource that you have already used in parts, namely for the parts of speech. Well, that was a clever pun had I intended it. Of which you have used parts, namely the parts of speech in the most recent assignment. And from the availability of 1 million words of running text of English with gold standards syntax trees, we then very straightforwardly derived the notion of estimating a probability distribution over the trees generated by a context-free grammar by associating the probabilities with each of the rules and using the chain rule. So fairly familiar application of known techniques at this point. Then we started to actually talk about parsing algorithms and looked at the, I believe, most simple algorithm conceivable, the recursive descent parser. That starts from the start symbol and generates trees and hopes to find the actual string eventually, and observed that the algorithm has exponential complexity because it's naive, but that also the problem actually has an exponential growth in it because the number of different trees grows exponentially in the length of the input. And then we introduced a key notion about local ambiguity that I'll briefly flash at you on the next slide, and started to look at our first application of dynamic programming to deal with that exponential growth, to get back into tractable computing space. So today we'll generalize the CKY algorithm into this more general framework, generalized chart parsing. We'll spend some time looking at the depth of the parse forest, specifics of these representations that you will actually build in the final assignment, and then actually not use a lot of time to adapt Viterbi decoding to the parse forest, to this structured space, and wrap up talking about parser evaluation, and then you'll have all of the pieces to write your own PTB, or PTB trained PCFG parser and measure its performance. So very briefly, refreshing terminology. Context-free grammar is a quadruple. We have the non-terminals C or categories, the terminals or vocabulary. We have the productions or rewrite rules, and we have the start symbol. And generally we say the productions can have the form 1 non-terminal alpha element C rewrites as any sequence of beta 1 to beta n from the union of C and sigma, which in principle could also be the empty sequence here. So this is the general form of context-free grammar. We looked at this beautiful graph for quite some time and observed that there are two different readings, but they both come to calling the entire substring boys with hats from France an NP. So they are different structures that assign or derive the same category for this substring. And for the purpose of parsing a larger sentence that contains this substring, say as the object NP, as in I adore boys with hats from France, it's immaterial whether the hats or the boys are French. All we need to know is that there's the possibility of calling this substring an NP. And this representation is what we call a parse forest because it represents multiple trees. And putting just one NP edge number 9 here, even though there are two ways of computing that edge by a combination of 1 plus 8 or 6 plus 5, so in each case one NP followed by one PP, putting just one entry there means here we break the combinatorics. That's where we stop the cross multiplication of ambiguity that gives us the exponential growth. So that's a key technique to making parsing with ambiguous context-free grammars, or parsing ambiguous languages using context-free grammars, tractable. And then towards the end of the session we introduced the Koch-Kasami-Younger algorithm, and its purpose is to fill in a tabular version of the same data structure where each cell corresponds to a substring of input. For example, here in red, 1, 2, 5 corresponds to adored snow in Oslo. What we count are 0, 1, 2, 3, 4, 5. The vertices, the inner word spaces, as we did here. Only here we're assuming there's room for another 2 preceding words. And then each cell is a set of categories that I can derive for this substring. And the set metaphor gives us that bounding of ambiguity because we'll not put multiple entries of S or VP or anything into the cell. When there are multiple ways of deriving the same category, we'll just record one. We know that there is an ambiguity in this sentence. Kim adored snow in Oslo. And where does that ambiguity reside in the chart, in this table? We can't see it because we're not putting multiple entries for local ambiguity. But where is the local ambiguity? So you're saying if we were to figure out the path from the start symbol to the leaves or the pre-terminal tags, then there would be two different paths somewhere. And effectively, each such set of paths would be a tree, a complete tree. So if we were to extract the complete trees from the forest, then there would be two. That is correct. And that would be a good procedure to work out where we actually branch off, where there was local ambiguity. I was hoping that you could sort of apply your knowledge of English and context-free grammar and observe it in this picture. Yes? Let's see, let me try to point at the cells that you're mentioning. So you're saying the local ambiguity is hiding here. And it's not just red because this tells us the correspondence to the substring. It's also red because it answers the question he was going to ask. That's very good reasoning. May or may not be true. And you're saying to put VP here, there are essentially two ways of combining other cells, namely which VP? 1, 2, 3. This VP? 2, 5 or 3, 5. Okay. So first of all, you're assuming that we have a rule that says VP followed by NP combines to VP. That's actually not the case. So when we have the when the verb has combined with a noun phrase, then that thing we call a VP. Furthermore, you were saying this VP plus this NP can combine. Now remember that to combine things, they need to be what we call adjacent. They need to be next to each other. And each cell corresponds to substrings. So this VP cell here corresponds to 1, 2, 3, adored snow. And this NP cell here corresponds to 2, 2, 5. 0, 1, 2, 2, 5, snow in Oslo. So this VP and this NP actually overlap in terms of the substrings. As a rule of thumb, to combine two cells, the row index of the second cell needs to be the column index of the first cell. That's how they sort of add up to a larger substring. So 1, 2, 3 could only combine with things that start in 3. And you had actually one good candidate here. So VP plus PP. We have a rule for that, and we can call that a VP. Because we can have as many PPs as the language, well, as we pick. We used that artificial example last week to observe the exponential growth. So here we actually have one VP plus PP, two cells that jointly add up to a contiguous string from 1 to 5 and derive VP. So we have one reason to put VP here. But to validate your hypothesis that this is red because it answers my second question, we need another such way. Which V? Well, there's only one V, so I'll make that easy for you. And which NP can combine with this V? So this V is, well, we only have one verb, adored. And now we want something that starts where this verb ends, so this row. And we want something that goes all the way to the end of the sentence and sort of has the same end position as this cell that we're currently computing. So this V plus this NP add up to 1, 2, 5, with 2 as the intermediate breaking point. And we have a rule V plus NP gives a VP, and hence we have validated your collective jointly, we have validated your hypothesis that the local ambiguity is indeed hiding here. So if we were not using the set metaphor for our cells in the table, we could have 2 VP nodes here. But then we would be back to the combinatorics we don't want. So that's an essential observation. That's something you absolutely need to drive home, how to read the start end indices and how to reason over 2 entries in this table that sort of graphically are not next to each other, but that in terms of the strings that they analyze, the substrings that they analyze, are contiguous or adjacent and add up to a larger span. That's at the core of this algorithm. We initialize the bottom diagonal, and then we compute one diagonal at a time. And each diagonal, as we move upwards, will have an increasing length. So down here we have strings of length 1. Here we have strings of length 2, 3, 4, and 5. This is the cell that accounts for everything. And the L here ranges over the length minus 1 because to make the indexing work out nicely, so this cannot start from 2 as I was asking myself semi-quietly last week. This has to start from 1 because down here we actually say the cell that we currently compute starts at I and ends at I plus L plus 1. That's a matter of convenience to make the other indices count nicely to reduce the number of terms. And then the I will be the start of the range that we're considering, and so I from I to I plus L plus 1 is the substring that we're currently trying to analyze, and J is what is often called the breaking point. It's where 2 cells become adjacent, as we had seen here. So this verb 1, 2, 2 and this NP 2, 2, 5 can combine, and here the breaking point would be at 2. And we just compute these essentially 6 indices into the table, the start and end of the cell that we're seeking to fill, the start and end of one cell, and the start and end of another cell where the 2 letter cells jointly combine to add up to the larger cell, the target cell. So one target cell, these indices, and 2 source cells, these indices, and then we just ask, do we have a production that has beta 1, beta 2 on the right hand side, where beta 1 is in the first source cell, beta 2 is in the second source cell? If so, if we have such a production, then alpha goes into the target cell. That's what we're doing here. So we union a new category into the target cell if and only if we can find a rule that rewrites alpha as beta 1, beta 2, and we can find beta 1 in source cell 1 and beta 2 in source cell 2. So to compute this VP, source cell 1 would be here, beta 1 would be V, source cell 2 would be here, and the rule would be VP goes to VNP, and hence alpha goes here. All right, that's the CKY algorithm. It just, in one pass, one upwards path fills in the upper half diagonal of this table. And at the end of the day, we can look here and ask, do we have the start symbol in the cell that corresponds to the entire input? If so, we have successfully parsed the input. We know that this string is part of the language. If not, it isn't. What we have not computed is an actual tree. We have computed a forest. In fact, a somewhat underspecified forest. All right, let me observe some limitations of the CKY algorithm. The attempt to combine two things to derive a new category always looks for rules of this form. Alpha rewrites as beta 1, beta 2. So binary, exactly two elements on the right-hand side. And, well, or alpha rewrites as gamma, where this was the initialization step for the lexical rules. But once we have that, for all remaining computation, we're looking for exactly two non-terminals, beta 1, beta 2. This is a more restricted form of context-free grammar than what I had on the original slide here, because here I said beta 1 to beta n, and they can be from the union of C or sigma. So the CKY algorithm is limited to a subset or a restricted form of context-free grammars known as Chomsky normal form grammars, where all rules either have two and exactly two non-terminal symbols on the right-hand side or exactly one terminal symbol. That's a restricted class of context-free grammars. And for natural languages, this is often an artificial restriction. So for example, we have verbs like give. I gave Sandy a book. It's very tempting to say V plus NP plus NP. V plus 2 NPs becomes a VP, because both Sandy and book are objects to give. And we couldn't do that in this framework. Furthermore, if we think about the order of computation, then CKY is breadth first or exhaustive in the sense that we need to be sure that we have all possible assignments for the lower diagonals before we can move on to the next diagonal. That's the prerequisite or precondition for taking just one path. So the algorithm will only be correct if at the time that I'm trying to put something here, I can be confident that everything that can possibly be put here and here has been found. So it needs to exhaustively analyze all shorter strings before it can move on to longer strings. That's this property. And this is closely related. It has a rigid control structure. It has to compute things in exactly this order. So this means it has to actually consider all ambiguity before it can talk about the string as a whole. And this means it furthermore has to do that in one fixed, rigid order of computation. So it's not a very flexible algorithm. And hence we'll now generalize it and introduce one additional notion. And that will have many good effects. So we'll preserve the strong points of the CKY algorithm, but remove all of these limitations. So we'll liberate the order of computation. We'll produce a variant of the algorithm where it doesn't matter in which order I compute cells, and where in principle I could introduce a notion of best first search, Remember we said the linguist is often interested in all trees. The application builder typically isn't. We will very soon put a notion of probabilities over our trees. So having to compute all of them to then eventually just pick the one that is most probable is not the most elegant approach, or the most, not necessarily the most efficient approach. So being able to vary the order of computation is an advantage. What we need to introduce is a notion of partially instantiated rules. And this notion is what we'll call active edges, that essentially have found part of the right-hand side requirements of a production rule and are still looking for others. And this dot is the notation that we introduce for that. So this is essentially an application of the rule VP goes to V NP, where what we have found so far is a V, but we haven't found the NP. This is an intermediate state of computation. These are the start and the end vertices, so this is essentially a doors, hoping to become a VP if only it could find an NP starting at position 2. So an active edge is an intermediate state of computation that we will make explicit in the chart in our table. And that's the main ingredient that allows us to work around all of these limitations. Now the parser can fill in chart cells in any order and still guarantee completeness. And let's see how that works. So in part to take stock in terminology at this point. So the chart is that table. It records partial analyses. We are indexing by string positions, where what we count are the inter-word vertices, starting from 0 conventionally. That is common for the CKY algorithm and for generalized chart parsing. For each entry, the row is the substring start, and the column is the substring end vertex. And each entry has a set behavior. We make sure to bound or pack local ambiguity by treating multiple ways of deriving the same category for one substring. That's what we call local ambiguity. And we treat multiple such ways as equivalent and pursue only one of them, or pursue such a set of multiple ways only once when combining with other constituents. And this gives us dynamic programming and memorization. There won't be any recomputation of results. The indexing into the memorization storage, the chart, is efficient by start and end positions, by integers. And effectively, we'll compute, as we did in the CKY case already, so we're preserving all of the benefits of the CKY algorithm here, a parse forest in polynomial time. And the parse forest is, you could say, a code for the set of trees that can potentially grow exponentially in the length of the input. I didn't comment on the polynomial time, but if we did the big O analysis, there are 3 nested loops, and they're all bound by maximum the length of the input. So if n is the length of the input, then we get n cubed as the time complexity bound for the CKY algorithm. And we'll again preserve that in the generalization. So this is beginning to be repetitive, but now an edge is a possibly partial rule instantiation. So the edges are the entries in the chart cells. In these chart indices, we sometimes call vertices. Then we have this ballistic diagram with the rounded arcs in mind. When we say indices, we have the matrix view as a table in mind. And the dot in somewhere between the beta 1 to beta n of a right-hand side of a production rule indicates the degree of completion. Where the dot is followed by more category symbols of the right-hand side, this is what we call an active or incomplete edge or item. It's still looking for something. The rule, we haven't found all of the pieces. And where the dot is at the end of the right-hand side, so this is also an instance of the VP goes to V followed by NP rule. But here we have now actually found both elements of the right-hand side. So the dot is at the end of the right-hand side, and that's a complete or passive edge. It's no longer looking for something. And then we can actually, well, algebraically, if you will, characterize the parsing problem in terms of what is often called the fundamental rule. And this may look, so you can look at this as an inference rule over the items or edges in the chart, but it actually looks much more mathematic than it is at its core. Well, no, it's reasonably simple, I think. You know everything that is written down in formal terms here already. So this rule says that I can derive new edges, that's what we get here, from the combination of two edges. So still, the computation will be broken down into binary combinations. But because we now have intermediate states of instantiating rule, we're no longer limited to binary rules. We can find one element of the right-hand side at a time. And the two edges that can combine using the fundamental rule need to satisfy the following requirements. Remember, this is start and end for each edge. So there's one edge from I to j and another edge from j to k. This is what I call adjacent. The second edge here starts at the position where the first edge ends. They jointly add up to a larger string. They don't overlap, there's nothing in between. Furthermore, the first edge is active. It still is looking for something. And finally, what the second edge is passive. It's no longer looking for something. And what the active edge is looking for as the next element on its right-hand side is the same category, beta I, that the passive edge has found or derived, has as its left-hand side. So one active edge plus one passive edge that are right next to each other, where the active edge is looking exactly for what the passive edge provides. When these conditions are met, then we can combine these two. We derive a new edge from I to k, the sum of the two substrings, and we advance the dot in the right-hand side of the active edge. We have now found the beta I, and we're looking for the next element of the right-hand side. What happens in this process is, of course, we push the dot rightwards, and eventually the active edge will become a passive edge. So in principle, in this notation, beta I plus 1 to beta n can be the empty string. So n can be I. And then what is the result of this combination would be a passive edge. The fundamental rule creates active or passive edges. That depends on the number of categories remaining after the dot in the active edge. And it makes sure that the things add up nicely in terms of the substrings that they cover and that they are compatible with each other. For many years, I used to offer the metaphor of dating for this process. I used to live in the US at one point, in California, and dating was a big topic there. And I still think they're useful analogies or parallels here. So you often have one active part and one passive part. And to add up two items to a pair, they need to be compatible. So when there is one active part, the passive part should have the properties, the category that the active part is looking for. I think I'll leave the metaphor there. It's sometimes been suggested that it's not perfectly appropriate in Norway to introduce the dating metaphor into chart parsing. But I hope you see effectively what the fundamental rule tells us about the algebraic process of deriving items or edges in the parse chart. Any questions at this point about the fundamental rule, not about dating? I wouldn't be considered a useful source, I think, on that topic. Here, yes?
Yeah, so you know you're looking for an NP.
Yes.
If there was a rule saying you can go from V to something else,
Yeah.
like to part of it.
Exactly, yes. So the active item records, I did say, an intermediate state of computation. And the intermediate state of computation is actually saying, I'll try to instantiate this specific rule at this point. So I'll see whether I can derive a VP from the combination of V plus NP. If there are other rules that might be applicable, then these will give rise to active items of their own. Effectively, I'm binarizing the combination. So in the CKY algorithm, it was by nature binary because I was restricting my rules to exactly 2 right-hand side elements. Now I'm back to allowing any sequence here. But I have a mechanism, I've introduced a mechanism to record, to make explicit, and to memorize any intermediate combination that results from picking a rule and beginning to tick off the right-hand side categories that it is looking for. All right, so here's an example of a both near and over complete chart, Kimmedore's snow in Oslo. And here I'm now showing the active and passive edges. So here I have not only S as the analysis for the whole string, but I'm also writing down, I've recorded which rule I used to arrive here. And here, in red again, I've actually recorded the local ambiguity. So I have a duplicate entry here that says, from 1 to 5, I can successfully derive a passive edge by either combining VP plus, or using the rule VP goes to VP PP, or using the rule VP goes to VNP. These two, so in this sense the chart is over complete, these two would be packed into a single entry. So here I've written down the local ambiguity. So it's important to note that the chart is over complete in this respect. I have active edges here, so here I should be able to trace, for example, the 2 edges from which this passive edge was derived. Shall we go hunt for them? Let's do that. So where do you think are the 2 edges from which this edge was derived? Let's go back to the fundamental rule. What do I know about these 2 edges? Use the dating metaphor if it helps. And they need to be in the same bar. Okay, so let's hunt for one active edge. So this is what we're trying to reason, we're trying to explain how our inference system, if you will, arrived at this entry here in the chart. So we're looking for one active edge that could have given rise to this. That almost has to mean that we're looking for an edge that says VP goes to VP dot PP. And where should that edge be located? It has to cover some prefix of the string from 1 to 5. So somewhere in this row. I think we found a good candidate here. So this this active edge here, if only it found a PP, could extend to this passive edge. So now we're looking for a passive PP edge that is adjacent to this active edge. So 3 there. It appears to be true. It's a date. Sorry, I just can't let go of that metaphor. All right, so this is what happens here. It's also near complete because I am missing some active edges, and I'm showing you what is effectively a cute formal trick and not something that we'll want to do implementation-wise. What I've done here is I've shortened our string for space reason. So now we're looking at Kim adores snow, just 3 tokens. And I've added one diagonal to my chart corresponding to empty strings, 0 to 0. There's no word there, so that's the empty string preceding Kim. 1 to 1 is the empty string between Kim and adores. And in these cells, I have now put active edges that effectively correspond to the grammar rules. Active edges that have not found anything yet. And with this addition, I can now, so what I'm doing is I include all grammar rules as what we call epsilon edges. Epsilon because epsilon denotes the empty string. So active edges where the dot is at the far left of the right-hand side, where the dot precedes the beta 1 of the right-hand side. And I've put those into each chart II cell, the chart cells that correspond to empty strings. And now all I need to do, so this is my initialization step, is to run the fundamental rule until the fixed point is reached. That means until I can no longer derive new edges. Are you following this? It's a cute trick. It's not what I recommend for implementation because we'll want to use more efficient ways of deciding where to actually introduce active edges. So well, as it so happens, there are no obvious cases of useless epsilon edges. Well, I only put those, so in principle, if I put all grammar rules into the chart, then I should also have VP goes to VP PP here, right? I've actually only put those into the chart cells that are useful at that position. So I'm not showing you all of the epsilon edges. To actually do what I say down here, let's say I have 7 rules in my grammar. I would put 7 such epsilon active edges into each cell in this lower diagonal. And many of them would be useless because they would be looking, so for example, if I put VP goes to VP PP also here, then to go anywhere, I would need a VP immediately to my right, that is sentence initially. And I'll never find that for this string, because what I have as the first word is Kim and not a verb. So that is not the most efficient way of introducing active edges. There will be many more active edges here than actually have the possibility to go on a date. But it's I like it because to me it nicely demonstrates the power of the fundamental rule. So in a sense, my entire parsing algorithm now is reduced to this inference rule, the fundamental rule. So this is the generalization we were aiming for. And this until a fixed point is reached is the key to liberating the order of computation. But I think that is where we'll resume after the break. Since you're so quiet, I'll just resume. One of you had asked whether our recommendation to use logarithm addition instead of multiplication for efficiency gains actually still holds true on current hardware architectures, and the answer is less obvious, I believe, than it was 10 or 20 years ago when I first learned that rule of thumb. It's certainly still the case that when dealing with probabilities and repeatedly multiplying very small numbers, there is a genuine risk of moving towards so close to zero that a machine float no longer has enough numeric precision to represent these increasingly small probabilities. And so that risk, the staying away from numeric underflow, I believe is still very much true and still a clear benefit in using log probabilities rather than raw probabilities. The efficiency gain, this thread says there's no one obvious answer, essentially. So there used to be one obvious answer, and that is not necessarily the case today. It's still a good technique to apply, but maybe only for one obvious reason now, where it used to be two obvious reasons. But we were going to talk about an actual algorithm. So here I had gone sort of lofty and nice and said, oh, here's a deduction system, and this is our entire parsing algorithm. But there's a lot of interesting algorithmic detail hiding in this until a fixed point is reached. So let's recall our abstract goal is to check all pairs of adjacent edges to make sure that the fundamental rule has been tried on all applicable candidate pairs of active and passive edges. So naive strategy could iterate through the complete chart over and over again, combining all possible pairs until no additional edges can be derived. Keep in mind we don't want to make assumptions about the order of computation. So we can't be sure whether everything that could be computed for this substring is already in place or not. We want to eliminate that limitation in the CKY algorithm. This would obviously lead to frequent attempts to combine the same pair multiple times, and we would have to somehow guard against deriving duplicates. So this is a truly naive strategy. The reasonably obvious approach to actually solving this problem algorithmically is to add an agenda, a to-do list of remaining work in the parser to be executed or computed, and see to it that for each pair of edges we'll attempt their combination exactly once. That is, we'll evaluate each pair against the fundamental rule once. And that can only be when both elements are available. Can't try a pair of edges when only one of them is available. And so what we do is new edges, so the result of a successful application of the fundamental rule, go onto the agenda. They still have to be checked against what is in the chart at the time when they come off the agenda. They have yet to be submitted to the fundamental rule. Look, I'm almost succeeding in staying away from the dating metaphor. When they come off the agenda, I'll try that new edge against everything that is in the chart at the time. And at the same time, I'll add it to the chart. So from now on, so it has now tried itself against everything that was available when, I'm not saying entered, it entered the bar. When it when it first came off the agenda, when it first started to be a real citizen, and we'll schedule all such attempts, new edge against everything that was available at the time in the agenda. And then we'll make that new edge available for attempts to combine with future new edges. So we'll put it into the chart. And this strategy I can prove formally will see to it that all pairs are tested exactly once. We'll not apply that proof. So that is effectively all we need, the combination of a chart and an agenda to achieve the goals that we set out in wanting to generalize the CKY algorithm to generalized chart parsing. Now we are free to design an agenda that gives us the order of computation that we find most beneficial. For example, we could make the agenda a priority queue and try to operate on high probability edges early. So active edges plus agenda are the two additions to the CKY algorithm that give us generalized chart parsing. Quite an influential paradigm in natural language processing. Natural language parsing, not so much in parsing of formal languages where there is no ambiguity. All right, now some technicalities. So we're constructing a forest, and we started out just putting the category symbols in the table, but we already started talking about, we still have that desire for trees. We don't want to know, yeah, this is a sentence. We want to know it's a sentence and it has the following internal structure. This NP daughter to the S is most likely the subject. This VP is headed by this verb, which is the main predicate in this sentence. This is how we work out how, well, who did what to whom. So we started on this route to actually compute syntactic structures. So far what we have, or the CKY algorithm as presented, is a recognizer. It tells us this string is part of the language or not. But it actually doesn't give us the string, it gives us the forest. And somewhere in the forest, I said there is this code to the set of trees. Now let's talk about how that code can actually be made practical in terms of writing our own parser. And we'll use a technique that in a somewhat similar application we used in the Viterbi algorithm, but it's a slightly, it's a loose parallel. We'll start to keep track not of the categories that we have found, but of the passive edges that served to allow us to advance the dot. So these numbers here are now edge identifiers. And here we have a passive edge that records Kimodor's snow, so no ambiguity, conveniently. Shorter example. This records that it was built from edges 11 and 13, and we can now go find these in the chart. And 11 better be an and both of these are passive edges. So they report at each point of using the fundamental rule, which passive edge was the second part, satisfied one of the requirements. And we can look up 11, so 11 is a V, and we can look up 13, that's an NP, and we can recover that this is an instance of the rule VP goes to VNP. But we have much more information now because this edge here effectively records a local subtree. I can chain down these backpointers and sort of pull one of the edges out and then follow will all edges that are linked to it by backpointers. And that will be effectively a tree. And that tree will be composed entirely of passive edges because only those constitute or correspond to complete subtrees. The active edges were very useful to us, but they record intermediate points of computation. They cannot be part of a complete result. A complete result has to be composed entirely of passive edges. So back pointers to daughters gives us the linkage. It's the result of an application of the fundamental rule. So let's look at an active edge maybe. So the active edges have back pointers preceding the dot and categories following the dot. And so all the fundamental rule cares about is start, end, implicit here in the row and column indices. The beta I that the active edge is looking for, and the alpha that the passive one is providing. I've not changed those. So those pieces of the edge that the fundamental rule cares about are still what they used to be. It's only where I advance the dot that rather than recording, I found an NP, I record more. I record, I found edge number 13, which has as its left-hand side category 13 alpha, the category NP that I was looking for. So I strongly record more information. How do I get the local ambiguity factoring? It still has to be the case that there is a set metaphor for each cell. I don't want to end up with multiple entries that have the same left-hand side category alpha. But what I can do is I can have a single edge represent multiple derivations. That is, a single edge can have a single passive edge, has its category alpha, and it can have a set of backpointer sequences. And that means a single edge can correspond to more than one subtree. But to active edges, it will look just like one passive edge to consume. So this will actually give me the bounding, the factoring of ambiguity. Here's the general idea. So for each category alpha from I to j, a substring, I'll maintain only one edge in the chart, and I'll sometimes call that the representative edge. That edge represents potentially a set of structurally different analyses for the same substring that derive the same category alpha. And I'll record all of these alternate sequences of daughters in the representative. I can have more than one record of how I managed to prove the right-hand side of the rule that this edge instantiates. So each edge instantiates one specific rule, but when there were multiple ways of doing so over substring I to j, then there will be multiple backpointer sequences in that edge. And to make implementation even more straightforward, so logically or conceptually what we're doing here is we group passive edges into equivalence classes by identity of alpha, I, and j. That's the notion of equivalence classes recovers the set metaphor in each of the cells. I and j define a cell, and alpha is the category. And before we add a new edge to the chart, we first search for an equivalent edge. Let's say we call it H, host, or maybe could have been R, the representative. And when we find such an edge, that means, what does that mean? What is it that we have just found? What has just happened? You said I should not answer my own questions. So under which circumstances, but I can help you answer my questions. Under which circumstances will it be the case that for a substring I to j, we have just computed or derived a new edge of category alpha, And the chart already contains, for the same substring, an edge of that category. We even have a name for that situation. Yes, and the name we have repeatedly used is local ambiguity. But so it's local to I to the substring I to j. Yes, it's ambiguity. So we have just found another way of assigning the same category alpha to the substring I to j. That was our definition of local ambiguity. And where that is the case, we want to maintain this unique representative invariant. So we're not adding e to the chart and will not process it any further. But we'll record the daughter sequence that E represents, the backpointer sequence, in the set of backpointers for H. So we keep track of the subtree, but we do so in the one representative edge. Crucially, no further processing of E. Why is that unnecessary? Because we have an edge H in the chart already, and our agenda guarantees that we will attempt all possible combinations of H using the fundamental rule against any other edge that will be computed. H is equivalent, so it has the same alpha I and j. That means for the purpose of using the fundamental rule, H and E are interchangeable. Anything I could hope to parse using E, I will already find using H. So I adore boys with hats from France. Boys with hats from France is an NP. And there are two ways of deriving that category. I find one first, that goes into the chart. Let's say these are the French boys. And using that addition in the chart, that says NP from 2 to whatever, 9 was it? 11 maybe? The category assignment NP to boys with hats from France is enough to parse the remainder of the sentence. I adore, so adore, NP, V, NP, that's a VP, and so on. Now, at some point in time, possibly after I've actually parsed the entire sentence, we can compute in any order, I discover that also the hats can be French. But all that gives me is another way of assigning NP to that same substring, and I discover actually there is an edge in the chart representing this category assignment. And then I'll not search for new sentence structures given the new hypothesis about the internal structure of that NP, boys with hats from France. But I will record that actually also the hats could have been French. So I'll record the internal structure, but I don't cross-multiply it with anything outside of the context of that local ambiguity. And this is what we've at times called a maximally specific forest. It's still a forest. I can still compute it in polynomial time, but it has, using backpointers and sets of alternate backpointer sequences, it has all the information I need to extract trees. That procedure is often called unpacking because we pack local ambiguity. That's what happens here. Pack E into H to record equivalence. And unpacking means to multiply out alternative daughters for all result edges. So an exhaustive unpacking procedure would be just to recursively walk down the tree that is the linked set of passive edges that ended up in the chart, and at each point cross-multiply. But we will soon see that exhaustive unpacking is typically not what we want to do. So here is an example, a hypothetical parse forest. So don't try to connect this to um, snow in Oslo. And we have different notions here. The ovals represent equivalence. So we know that 6 and 7 are edges at the same span, start and end vertex, and of the same left-hand side category alpha. The dotted lines are daughter relations. So 10 is the sole daughter to 6, and 4, so these are the back pointers essentially. 4 has combined 8 plus 6 into one edge. Given this representation, could you say which of the edges are in the chart and which are not? Yes, you could. You know enough to answer that question. I'd bet every one of you a beer that you know enough, but I think that's an unethical bet. So I'm asking, can we say, given what I told you, equivalence relations and backpointer or mother-daughter relations in this forest, can we say which of these edges actually are in the chart, are representatives, and which are packed away? So you're saying, right. That's a very good answer, including one which doesn't meet your, so the root edge. So you're saying those edges that actually are daughters to another edge, they have to be in the chart because they have been arguments to the fundamental rule. They have been consumed by other edges. Because to be the daughter of another edge, to actually be back pointed to, means there was an active edge that found me. And hence, I'm redrawing the forest here, highlighting those that actually are in the chart. And now conceptually, so 2 is actually in the chart. I've used 2 to derive 1. I've combined 2 and 3, and that gave me 1. All of these are passive edges. We're not seeing the active edges. They were useful to us, but now we're done with them. They're in the chart, but we don't consider them. But because 4 was computed after 2, was found to be equivalent, 2 was the representative in the chart already, 4 was inserted into the same equivalence class. 4 had daughters of its own, so it represents its own set of backpointers. But 4 is not in the chart. But putting these 2 into an equivalence class means that for the purpose of combinatorics, I'll actually consider both 4 and 2 as daughters to 1. Yes? Yes. Against this recipe for implementation, no. Or one is directly in the chart, and the other one is inside of an edge that is in the chart. So it's not visible to others. It's not visible for further processing. That's true. So the information that E contributed is in the chart too, but for the purpose of the agenda strategy, what we consider is H. We only look at I, j, and alpha, and technically we do so on h. Because, yes, yes. So the back pointer in the forest, if we implement it that way, will go to 2. And 2 is h. We're not creating a new object x. We just keep the one that came along first and sort of augment it with the back pointers. And in fact, that augmentation, so pack e into h to record equivalence, will actually just have an object, a structure for the edge that has a slot, a list of equivalent edges, and we'll put the entire e in there. Even though all that we need e for now is its back pointer sequence. So the rest of e we could discard, but it's convenient. I mean, we have e already. Why not use it? So we're not creating unnecessary new structure. All right, so this is more like what we compute. This is how to interpret it. And now what does it mean to unpack, to cross-multiply the local ambiguity? So here I've done the unpacking at each local level, and again, I'm getting ready to ask a question. And I hope you can see that I'm getting much better at not answering my own questions. So brace yourselves. So same forest. And here I've now spelled out that this means that edge number 1 actually stands for 2 different daughter sequences, namely either 4 or 2 followed by 3. So it's the first daughter, the left daughter of 1 is packed. It actually represents more than one tree. The second daughter is not. And so that means conceptually 1 represents a set of trees where the subtree in its first daughter will be either one of the elements of the set of trees represented by 4 or the set of trees represented by 2. I talk so carefully about sets of trees because of course these edges also represent more than one tree. In principle, any edge in the chart can now represent a set of trees, a set of different subtrees. So let's look at 4. 4 can cross-multiply locally into 8 plus 6, or 8 plus 7, or 9 plus 6, or 9 plus 7. So 4 by itself represents 4 different local cross products. And now I'm asking, how many complete trees does this forest actually contain? Used to be one of my favorite exam questions. But that's maybe because I did my own dissertation in this space. 32. Wow, how do you arrive at that number? Only for one of them? You're on the certainly on the right path here. You're doing exactly what you introduced earlier. You're constructing path connecting the root node to the leaves. So you're saying from 1 I can go down to 2 and 3, and 2 actually stands for at least these 2. And among these 2, 6 stands for 2. So that means for this pairing, 5 and 6, this actually represents 2 trees. Stian. Yeah.
And each of those places, there are two choices.
Talking about this equivalence class,
Yes, there are three.
I'm giving you 4 different sequences of back pointers here.
But from that very equivalence class, I can choose any of those two numbers.
Yeah, but so at the end of the day, now we're asking for complete trees where there are no longer equivalence relations,
So
no packed ambiguity.
I think 16 would be the answer.
Okay, we're working downwards. Have you updated your estimate? But you're both on the right track here. So we could write next to each oval the number of trees represented by the oval. That would be 2 here.
What I really mean is that say that you do pick one member from each equivalence class and write it beside it, and you have a complete tree.
Then you have 1 complete tree.
You have one complete tree, and if you do other possible
Yes,
ones, then you are happy.
exactly. And how many trees will that procedure give us?
Well, since
9. Can you?
If you
I'll point for you.
if you have if you just keep the root tree
Yeah.
and you go say you go for 2 3, that represents the 2 represents 2 choices.
Yeah.
So you have 2 trees where the 6 is 2 choices.
Yeah.
So that's if you just look at root 1 2 3, that is 3 trees in total.
Yeah. So 6 is 2. 6 is 2 subtrees. That means here we actually are looking at 2 subtrees
Yeah.
plus 1. So 2 corresponds to 3 subtrees.
Yeah.
That's what you're saying.
And then if you instead of the 2, you go to the 4 from the root.
So 2 here is no 3 here. There's nothing happening here. So up here we have now 3 counted 3 subtrees.
Yeah.
And for this one,
You have
4, but 2 of them again include 6. So that's 2, 3, 5, 6. That means 6 here. 3 plus 6 is 9. No, I don't have a slide for that. Okay, that was a from my point of view, the high point of the semester. I would like everyone to make sure that you can follow this reasoning and that you understand this representation, because that's really the essence of generalized chart parsing and dynamic programming applied to parsing ambiguous languages using context-free grammars. If you can do this, and it's surprisingly hard conceptually, because they're recursive choice points, and we need to keep track of all of them and cross-multiply. So I've really given you here the recipe for doing that, or for the necessary bookkeeping, but still you need to do the recursive, in a sense, bottom-up addition. So we ended up asking, sort of being forced further inwards in the tree to actually come up with these numbers. So we had to say, okay, for 1 I need to go down to 2 and 3, and for 2 I need to go down to 5 and 6, and for 6 I go down to 2. And then I could come back up and say, okay, 6, that's 2, so this is 3, and so on. So and essentially the algorithm to add up the combinations would be a post-order traversal of this graph. So I still have one more topic I was hoping to cover today. We haven't talked about Viterbi, but fortunately it's easy. Maybe we can still squeeze it in. And then we'll have evaluation for next week. That's all the motivation for syntactic structure. I don't feel I need to say all of these things again. Tractability through packing of local ambiguity. Chart parsing is specialized dynamic programming, and the generalized chart parsing algorithm with active edges and an agenda gives us free order of computation. What is missing still is the one best efficient enumeration of the most probable parse tree. What we did here conceptually is exhaustive unpacking. So when we computed 9, we could as well have returned 9 complete trees. Rather than adding, we could have just put together those tree structures, coming back from the post-order traversal to the top. Okay, let's do this and then wrap up for today. Oh, I have some fluff here, some motivational fluff. Any non-toy grammar for natural language will give you tens, hundreds, thousands, actually rarely thousands, I would no longer say that today. Rarely billions maybe. But there can be tens of thousands of readings for a string of 20 words. And all legitimate. I have a close colleague who actually is a grammar writer, a computational linguist, who's been writing down the rules of English syntax for the past 25 years, and he says, well, you're right to observe that for this string I give you 28 trees. If you fly me out to a nice location, I'll be happy to explain every one of them. And at the end of the day, you'll find that all of them are grammatically legitimate. So we did have her report on my desk and arrived at 12, and they're all grammatically legitimate. Some are more plausible than others, but without knowledge about context and the world, grammatically they're all good. And identifying the intended analysis, what the speaker intended, well, we don't have access to the speaker's brain. So that's what we sometimes half-jokingly call an AI complete problem. We would need models and technologies that I don't expect we'll build in the foreseeable future. And what one used to do, this is a historic note mostly, what one used to do is say, well, I can make that space more tractable by saying it makes sense to subdivide the space of objects into physical objects and mental objects, and human or animate and inanimate objects. So devise an ontology of things, often called sorts of things. Then it would be tempting to say, well, the subject of the die relation, that has to be something that is animate. And that means I'll not require my parser to consider inanimate NPs in a subject position to a VP that is headed by the verb die. This would typically sort of come together at the level of logical form, as I showed 2 weeks ago. But projects die and computers die. So even tempting as it seemed for decades, these sort of constraints are not about grammar, they're about the world. And we are unboundedly creative in our use of natural language to talk about the world, the physical, real world, or also a hypothetical world. I mean, imagine fairy tale language where the cup walked up to the little princess and said, I can personify inanimate objects without much difficulty. So that strategy sort of was commonly applied up until the mid-1990s maybe. But that was before we actually had the training data and the mathematical models to do probabilistic ambiguity resolution. To you, now 20 years later, it's not a surprise that we'll say, okay, this identifying the right analysis problem we'll approximate as the most probable tree. That's what we've been doing repeatedly. So we'll design and use statistical models to select among competing analyses, and we actually have one such model already, probabilistic context-free grammars. And then we'll maximize for string S among the set of trees Ti and look for the tree that has the maximum conditional probability given S. And that's our formalism that we'll use. Oh boy. I think I'll come back to that in our this is the I'll come back to the reflections on probabilities and natural language next week. But I want to go through this slide. So this is just the pseudocode of the generalized chart parser. And here is what we've done in terms of Viterbi decoding over sequences so far, where V at time point I for state X was the state matrix caching previous computations. In the parse forest, we no longer have a linear order. But given the explicit nature of the forest and the backpointers, we have complete structural information to work out the right succession or sequence of computations to play the very same trick. So for a given edge E, we will assign to it the maximum probability for any subtree represented by that edge. So the edge can represent any number of trees. Each tree will have a probability, and V of E, we want to be the probability of the highest scoring tree represented by that edge. And the probability of a subtree we can easily compute from the probability of the rule that this local subtree has instantiated. So this is the rule probability, beta 1 to beta n given alpha. These are the probabilities we estimated from the PTB. Times the maximum probability of any of the daughter edges. Or the maximum probability of deriving beta I for all I between 1 and n as daughters in this configuration. So here we get the same recursive decomposition, and we get the same nested requirement to sort of walk inside into the tree to determine these values as we come back up. So again, this will be a post-order traversal, the same order of computation as in counting the total number of trees, because we need to fill this I'll say matrix, but it doesn't have to be a table, the V of E matrix for the smallest subtrees first, to then compute the maximum probabilities for larger subtrees, including those smaller subtrees, as represented by each edge E in the forest, or each equivalence class. It's similar to HMM decoding, but the sort of sequence of filling in those values, so we play the same trick, we recursively decompose it, so that dynamic programming using this V of E cache becomes applicable. And the order of filling in that cache is now not determined by the sequence, but by the topology of the forest. And we also need to keep track of the set of daughters that led to the maximum probability. So again, we don't want to know that this is a sentence with probability 0.7. We want to know that here is a tree that has probability 0.7 and that is rooted in S. So we want to extract at each local point of optimization the subtree that maximized this term. So the argmax of, well, we don't have the TIs explicit here. And since we have the edge structures in our forest already, there will be a fairly straightforward implementation where we can just cache both the maximum probability among all subtrees represented by this edge and the local backpointer sequence that corresponds to that tree in the edges in the forest. This will become much clearer as you download the final problem set tonight and start working on it. You could do so tonight. You know almost everything you need to know to do that. And I'll see you again a week from now to wrap everything up nicely.